faculty members, and dear participants. I am Abhishek Pal, Head of the Department of Computer Science and Technology and Session Coordinator of this Faculty Development Program. On behalf of Dr. BCR Polytechnic, it is my great pleasure to extend a warm welcome to all of you to this Faculty Development Program on Applied Energy Engineering from Renewable Systems to Sustainable Practices. Before we begin today's proceedings, I would like to take a moment to acknowledge the platform that has brought us together. This Faculty Development Program is sponsored by AICTE Training and Learning Academy. The ATAL Academy was established with the vision of empowering faculty members across the country by providing high-quality training in emerging areas of technology, research, innovation, and professional development. We are immensely proud to host this program. The selection process for our AICTE ATAL FDP is highly competitive and rigorous. I am delighted to say that out of 1,768 proposals submitted from across the country, our proposal was among the select few that were approved. This achievement reflects the quality of the program we have designed and exceptional expertise of the distinguished resource persons who have graciously agreed to share their acknowledge with us. It's my absolute pleasure and privilege to introduce our guest and distinguished speaker for the session, Professor Dr. Sounak Roy. Professor Roy is currently serving as a professor in the Department of Chemistry and as the Dean of Research and Innovation at Pilani Hyderabad Campus. His academic journey began here in West Bengal. He earned his Bachelor of Science degree from the University of Bardhaman, followed by a Master of Science degree from the University of Kolkata. He subsequently completed his PhD at the prestigious Indian Institute of Science, Bangalore. Following his doctoral studies, Professor Roy further expanded his research horizons through postdoctoral research at internationally renowned institutions, including ETH Zurich, Switzerland, followed by the University of Pennsylvania and the University of Delaware, USA. His interest of research lie at the forefront of material science and environmental sustainability, with a particular focus on catalysis for alternative energy, nanomaterials, and solid-state inorganic chemistry. His outstanding contributions to the science have earned him numerous accolades. Most notably, in 2023, he was elected as a Fellow of the Royal Society. Request our Honorable Principal, Dr. Orijit Kumar Banerjee sir, to kindly felicitate our distinguished speaker as a token of our sincere gratitude and appreciation. To formally commence today's program, it is my proud privilege to invite our Honorable Principal, Dr. Orijit Kumar Banerjee, to address the gathering.
Good morning to all, everyone present here. Our respected Chief Guest along with that our first speaker, Dr. Sounak Roy. Like Dr. Abhishek Pal has told about his overall journey starting from West Bengal to his with Pilani Hyderabad. So having with us with in this field, that is the energy sustainability and climate change. First of all, welcome you all, the participating institutes, the faculty members from the BC Polytechnic, those who are present here. So under this theme that he has told that out of the various proposals that have been submitted to the AICTE, so out the total in India this year 379 has been accepted, and in West Bengal 12 proposals from the different institutes have been accepted, and out of these 12 from West Bengal, Dr. BC Polytechnic is one of them, and we are proud for that. The total committee who is working on it. So based on the theme, as we know, energy sustainability and climate change, recently throughout the world, the energy crisis is a major concern. Along with that, the climate change. So every day, because of the climate change, various issues, the landslides, the human health, the mental health, along with that, the total road infrastructure, everything is being collapsing throughout the world. Not only the energy crisis, that is the fuel. So based on this theme, it's the hour, need of the hour for such kind of FDP courses. The faculty members, not only we are teaching our students the courses from the curriculum, but also everywhere we have heard the term sustainability. So sustainability, to get a knowledge about the sustainability, the sustainable materials, the sustainable process, along with the course of 6 days, we are having the eminent speakers from different institutions. The Pilani Hyderabad, we are from NIT Durgapur, we are from CMERI, DPC, DPL, then TPSDI. So the different sessions are arranged in such a way that how the industry is adopting the sustainability, how the research is going on, the research throughout the globe or throughout the India, different institutions they are doing. Along with that, you all know that we are having a one-day session, half-day session to the TPSDI, that is the industrial visit, how they are doing also. So overall, I think that throughout the 6 days, you will enjoy all the different sessions and be cooperative with the speakers, be interactive, because without interaction, the exchange of the knowledge is not possible. So I wish this FDP a grand success, and thank you all for present here.
Thank you very much, sir, for your inspiring and encouraging words. They have truly set a positive tone for the program ahead. We shall now proceed to the first technical session of the day, titled Correlating Structure of Materials with Their Catalytic Properties. Ladies and gentlemen, please join me in giving a warm round of applause to Professor Dr. Sounak Roy. Sir, please.
A very good morning to all of you who are present here. Long introduction by the session coordinator was really embarrassing. But thank you so much for the kind introduction. Thank you so much, Professor Banerjee, for the invitation, and honor is so dear to me. It's very nice, and particularly I think I am coming from the furthest, right, among your list of the speakers. The special reason is that this is the place where I actually grew up. So any chance I get to come back to the city, I always. It's a wonderful initiative, and when I heard that there are so many proposals, that only a few of them have been awarded, and one of these from this particular college is really commendable, which shows the enthusiasm and the quality of the proposals which we have brought through. So congratulations to the people who were involved in shaping up the proposals and sending it to the AICTE. And to the rest of the audience, again, warm welcome to the day one. The title of the talk, which you said, is a little bit changed, because later I understood that I might be from the field of chemistry, but you should not be programming. You are not, right? So I tried to keep it very broad, so that we all can actually interact, and I can cater to each of you. And I made it a very short title, called Alternative Fuel. I will come to that one in a minute, but then I have a request to you all. Just stop me anytime you have a question or a comment. It need not be a question also, just a passing comment. I would just feel that probably I'm connecting with you, unless it would be just one-sided monologue, and I definitely would not enjoy that. Okay, so as I was introduced, that I come from BITS Pilani. I do not know how many of you know about BITS Pilani. It is one of the oldest private university. Long back, started in a small village in Rajasthan called Pilani, where the builders are actually. So 1964, it got the deemed to be university status, and at that time BITS Pilani made some commendable changes in its academic curriculum. It started in collaboration with MIT, so one of the few institutes in India probably who did it. The semester system was one of the things which we started at that time, and then the journey continued. In 2004, BITS Pilani stepped out of Rajasthan and went all the way to Middle East. So our second campus came in Dubai in 2004. Then the third campus came in Goa, BITS Pilani Goa campus, and then 2008 Hyderabad started. So in that way, Hyderabad campus is not that old per se. And then we also grew to some other places, one in Bombay, where we do not have the STEM courses, however we have the management and law, and a very greenfield campus is coming on in Amravati, in Andhra Pradesh. So in many places. And I particularly, though is from chemistry, but I work on the interface of material science and chemistry. And one of the interests is probably understanding the material's properties and use them as a catalyst for various kind of environmental reactions and the energy applications. Okay, now when I come to the topic of energy, which is is also one of the headings of the applied energy engineering and from renewable system to sustainability. And it's a very, very buzzword, right? Everywhere you go, it just people throw the word sustainability on the face. So let's go a little deeper to understand that where it stems from, where it's originated from. Maybe a little bit crowded slide, however, does not need to be delivered a lot because this is something which we already know. I mean, greenhouse gases, right? And they are constantly increasing, particularly the post-industrial era. The greenhouse gas significantly on the rise. And when you say the greenhouse gas, the first one comes as the carbon dioxide, the methane, the NOx, the nitrogen oxides. And it's not that it's not there before, but then when the urbanization started happening in a rapid pace, the industrialization started happening. Durgapur is one of the brightest examples of that in the eastern part of the country. A huge amount of anthropogenic carbon dioxide started emitting into the environment, right? And when I say anthropogenic, the carbon dioxide to some extent is the cycle, right? There is some kind of an equilibrium exists. We have to emit the carbon dioxide. It is also helping to grow the food from the plants and other things. But then the human created extra carbon dioxide started creating the problem. And by any chance, you know that how much amount of carbon dioxide now in the atmosphere? Any number probably you can throw to me that would help the conversation flowing.
0.04%.
1%, below 1%, 0.034 percentage. Okay, teeny bit of carbon dioxide, right? A huge amount of nitrogen, oxygen. You are talking of very, very less than 1% of this carbon dioxide, and that's creating the havoc. In terms of ppm, parts per million, it is 434, which was recorded by the Mauna Loa Observatory. The number as such looks very, very insignificant. But then the global temperature, the average temperature is on the rise. And for that, what's happening, the glaciers are melting, the sea level, mean sea level goes up. The coastal cities like Kolkata, Bombay probably will be underwater if we continue in this scale with this teeny tiny amount of carbon dioxide, right? Then another thing is that it causes the sudden weather changes. The El Nino and the El Nina, you have heard that the terrible weather in the winter probably, which is completely unexpected. The reason behind that is the greenhouse gas, the methane, the NOx, the carbon dioxide. And those we are actually responsible. The loss of the biodiversity, the floras, the faunas, and the various kind of biodiversity are actually diminishing, right? And then the last but not the least, the food security, the energy security are in the threat. We cannot just go ahead and do this. Does that mean that we shall not move towards urbanization or the industrialization? We have to, right? Because that's the civilization, the economics depends on that one. But then we probably need to find a sustainable route to see. I mean, we just cannot go back. There is a very small section of the paper, I do not know how many of you know, just below in the southern part of Philadelphia, Pennsylvania, in the Philadelphia state. They are called the Amish people. Somebody said, you know. Yeah. So you know what they do, you of course know. So basically, they say that no motorized thing. They still run the cycle, and the cycle does not have those the chains. So on the downhill, they just get into the cycle and go down. They don't shave the way. There is no use the foam environmental thing. But being in in America, which has the largest economy and every growth is coming from the country, there's a very small village who actually maintain that one. I got a chance to visit that place. The thing is that it cannot be a sustainable thing for the entire globe, right? We need to run the AC. And to run the AC, I need the power from the DVC or any thermal power plant. The moment I drag the power, I am actually emitting the carbon dioxide in the environment. So each of us in this room are actually responsible for these greenhouse gas emissions, the methane, the carbon dioxide, and the NOx. When you drive a vehicle, I believe that almost all of you probably have come to this place. Either you drove or you got a ride in a vehicle. The NOx emission is N2O. It's really harmful, right? And each of us are contributing in our own way to get that. But we cannot come out of this one. We have to move on. So the sustainable solutions, what we need to do.
একটু জোরে প্রেস
Directly
স্যার
to
না
that.
না স্যার একটু
Jore.
হ্যাঁ একটু জোরে প্রেস করুন
Okay. Now the thing is that I will give you some rough sketch, some numbers, because numbers give us some kind of an understanding that where from these huge greenhouse gases are coming from, right? I said you said 0.034 percentages of carbon dioxide. I told that in a specific number of parts per million. 620 exajoule is the amount of energy the world requires. Now, joule. Now it's an exajoule. And if you look at this side of the slide, okay, you would be seeing that 31% is coming from the crude oil. You just dig the oil, we get the energy of it, right? And you know which of the countries are actually very fortunate with the oils and they supply the crude oil to the rest of the world. 27% is from the coal. Again, you dig the coal, you burn it, huge amount of carbon dioxide from the boilers and the exhaust pipes come into the environment. 26% is the natural gas. Again, it's a greenhouse gas. We try to use it, the methane, which is already there. Whenever you dig oil, there is invariably there is a natural gas which is also lying into the oil well. So 26%. And look at the renewable source, the nuclear, the hydro, and we also have our inhibitions to go for the nuclear energy. Hydro is really, really small, energy-wise. So you can see that most of these things are basically the non-renewable sources. There's a word written renewable. You can see the 31 plus 26 plus 27, almost near to 90% are basically the non-renewable source of energy, right? And it's not only us, not India. This is the world data, okay? So you can understand that how much rampantly we are actually digging the earth and taking the oil out, taking the coal out. The twofold problem. The resources are depleting and we are polluting the environment. We are really, really responsible to kill this earth. India, on the other hand, do not have any oil source, right? You probably now heard of this conflict between the US and Iran, and all those vessels which are coming through the Hormuz and other things every day we see in the newspaper. We depend on them. Any change over there, our barrel crude oil price go up and it's going probably from our pocket, right? We do not have much control on the fact. But if you look at the percentage, which was 31%, it is actually less because we are constantly importing that one. And 56%, somehow India is blessed with coal. I was having the afternoon flight from Hyderabad to Durgapur yesterday. While getting down, I was seeing all the mines, open mines. One here on the right, a lot of coal, right? And this place is particularly in India is really replaced with coals. However, that coal is not sufficient enough to meet our requirement. We still import coal from other countries. The quality of the coal is not of that high grade. Okay, but look, just to save the economy and reduce the dependence over the on the foreign exchange and to the other sources, we depend heavily on our coal, which is 56%, which is different than the rest of the world over there. And less than 6% is a natural gas, and these are teeny tiny amount would do nothing for these billions of people. So basically all these 85 to 90% of these non-renewable sources of energy is contributing hugely the greenhouse gases in the environment. Now let me just try to focus on this part, that really these 25% is how much does that actually in number means to us. Now this graph, I do not know from the back if you can see the numbers. You do not, but let's look at the trend. These are the years. This is 2014. I'm going all the way to 23, 24. The latest data, 26, I do not have that. But you can probably see, if you do not see the number, doesn't matter. The numbers are really, really high. These are all million metric tons. So this number is 200, and this is on the steep rise, on a cumulative average growth of 2.6 to 2.9% of growth. There is a sudden drop in 2020. It's no surprise, you know, that we all hit. The COVID came in, and then all the industry shut down. We were not driving vehicles, we were not going out. So that demand came down a bit. But the moment the economy was stalled for a year, and then once it started again back, we are steadily growing. And then we crossed that 1920 data, 255 metric tons of demand, what we have now, right? How much are we actually bringing in? I will read the number for you. This is 255.7 million metric ton of crude oil demand in India. India in that particular year, 23-24, imported 231 million metric ton. So how much we still try to bring? This 25% I am talking, right? The rest are still the coal and all those things from where we are actually lighting our houses and running our ACs and whatnot. But still we cannot meet the demand, right? The demand is 2.9% against the 2.6%. Sorry, the import is a CAGR of 2.9%, which is higher than the demand, which is 2.6%, but still we cannot meet the import versus demand. The huge amount of the foreign exchange, basically, you do the hard-earned money, you pay the tax, and the tax goes to again bring your fuel. So the key highlights are that India brings around 85 to 90% of the crude oil, right? Only 10 to 15% probably we have. You know, we stand as the third largest oil importer in the globe. So we don't have any, but we are on the topmost layer, the third largest crude oil importer. As I said, the number is 255 million metric ton of demand and 230 million metric ton of import. So this threat is actually on the energy security. That if we depend on some other countries, of 85% of our energy depends on the other people's supply, right? So how much vulnerable are we? They stop, our energy goes away. It's not that by this vulnerability we are doing anything good to the environment. We are still polluting the environment. But even we are so vulnerable. And this is actually the precise reason of this all the geopolitics. Isn't it? I mean, it's very obvious that if USA puts a sanction that you cannot buy the oil from Russia, we would not know, because 85% of our dependence is from just somewhere, wherever the money, I mean, we spend the less foreign exchange. Right? Okay. So, and this is just, I'm talking of India. There are various other countries. I said the third largest importer, China is the first one in importing now. So the problems are that the rising global energy demand, and this demand will, of course will grow, right? Economy will boost. 15 years before probably you had only one AC, before that there was no AC, now you have multiple AC in 2 rooms. You have more than one vehicle in your house. I'm just talking about the domestic thing. So this energy will grow, the number of population is growing, the cities are expanding, the dependence on the fossil fuels are growing, the energy security is on risk, the geopolitical risks are there, the energy affordability is another thing. These are all very much tagged with your pocket, because the economics heavily depends on that, what is the affordability. Ultimately, that if I cannot buy the energy, if it is not affordable to me, and 85% I depend on other people, it's really a risky, and the economics is basically on working on a rope kind of a situation. The transition and the grid integration is another problem, the critical minerals and supply chains. I'll probably touch upon those parts slowly. So, there's a trilemma, it's not a dilemma, it's a trilemma kind of a thing, that the energy security has to be maintained, the balance of the environmental sustainability is the second one, and the energy affordability. So these 3 points has to meet to go for the particular word sustainable practices, right? Okay. Now so much of this combustion of the fossil fuels, the coals, the crude oils, it's not alone the India's problem, right? Or not at all China's problem. The story started, as I said, in the Industrial Revolution time from the Europe, from England, US. For over a long period of time, they were constantly producing the largest amount of carbon dioxide and throwing it to the air. Now probably we are stepping up and we are also contribute, but over the years we are not. And it's not that in this room we are discussing. The very first conference happened. The first World Climate Conference happened in Switzerland, in Geneva, in 1979. Okay. And then 9 years later, the IPCC, Intergovernmental Panel on Climate Change, who actually tells that what should be the permissible limit of your exhaust, right? Now you know that when you buy a vehicle in India, from BS6, now it's BS6, BS6. In Europe it is probably Euro 7 is on the run. And US has their own pollution control and other countries too. So that was the IPCC, which was created in 1988. And 1992, the United Nations Framework Convention of Climate Changes took place. Okay. And after that, the first legally binding treaty happened in Japan, in Kyoto, the Kyoto Protocol. It was mostly for the developed countries, the Europe and US, that how much should be the permissible limit from your exhaust for any thermal power plants or steel plants or the cement industries, that how much of the greenhouse gas can actually come out. Now, India was not a part of that one. Later, the Paris Agreement happened, and most of the countries actually accepted that one. So the term came as CBDR, common but differentiated responsibilities. Everyone is working towards the common goal, but each of them are having the different responsibilities to reach to that common goal. And this is not as simple as we were discussing maybe in 3-4 lines, because the major player basically controls the economy of the entire world, United States, have always gone for a yes and no kind of mode from the very beginning. I'm not here to criticize, but to state you some fact, US signed the Kyoto Protocol, and it was not ratified in the country when later when they went back. The Paris Agreement in 2015 was under Obama, and then when Obama went back, it was withdrawn at the time of Trump, the first. So it was always one step forward, two step backward by the largest contributor of the greenhouse gas. Now let's see where India stands. The BRICS conference, what happened in Rio, and again the COP26, what happened in Glasgow. India took a pledge that by 2070 we have to reach the net zero target. I'm sure all of you have heard the word net zero now. Now, what exactly does it mean? Is it that if we take the pledge, we will be achieving that? No. So it was broken down into 5 segments. 2070 final target is net zero. The 2030, India will increase its non-fossil energy capacity to 500 gigaton. Okay, so we will actually depend on the renewable sources, and we'll try to extract 500 gigaton of energy, gigawatt of energy by 4 years from now. Quite ambitious, right? 50% of the energy requirement from the renewable energy sources, and step by step, and finally going to 27. So, and the other countries like Brazil took the pledge by 2050. It will reach the net zero. Russia by 2060, China by 2060, India 2070, and South Africa by 2058. So among all the BRICS countries, India is taking the longest time probably, but then still, I will tell you that why it is not that easy. We are here at a place where the largest industry is the DSP, right? Durgapur steel plant, the steel authority of India. And India really is on the third or stands the third or fourth nation to export the steel to the rest of the world. Of course, the Steel Authority of India Limited, the Tata Steel, the JSW, who else? Sorry. Any question? I'm just only talking. If anything coming to your mind, just stop me. Anything? No? Okay. It's rainy outside, and
Who is the second importer?
second importer?
First importer is
China.
China.
Okay.
Third is India.
Third is India. Who's the second? Will you allow me to Google it? I do not know. Okay. But you can find out. Okay. So let me come to the now crux of the problem, that why the sustainability or going towards the renewable sources are so damn challenging. As I mentioned, particularly in the context of this geographical location, let me pick up the steel plant, right? And basically the process is that it's a very high energy, POF, and what happened? Okay, so it's the coke which is combusted with the oxygen to produce the CO, and the iron oxide is now reduced. The small chemistry, but then it does not happen in just writing on the board. It really requires very, very high temperature. Reacts with this CO, which is coming from the coal, and then reduces the iron oxide to iron. Steel is what? Iron and then some carbonate, right? Okay. Now the entire these steps, the picture is probably not seen at the back. So each of the step, the coke production step contributes 20% of the carbon dioxide emission. The sintering and the pelletization contributes to the 15% of the CO2 emission. The hot metal production, 25% of the CO2 production, that 426 ppm or 34 ppm, whatever I mentioned. The crude steel production is 15%. Can you guess that to produce 1 ton of steel, how much of carbon dioxide we produce? Any guess you can take? Take a guess, 1 ton of steel, how much, tell me in terms of tons. It's a 2.5 times amount of steel production. So to produce 1 ton of steel, we produce 2.5 tons of carbon dioxide. Isn't that number really, really mind-boggling? So this is the fiscal year 22, fiscal year 23 and 24. And this one I am talking about the crude steel, okay, which you cannot use. Then you have to make it to the fine steel. So the crude steel production, the numbers are 2.5, so basically 1 ton of steel emits 2.5 tons of carbon dioxide, crude steel. Again the number came down, went up, so basically in that range, 2.5. It's huge, right? More than your product, you are making the byproduct. And India, 4C, now it's a 300 million ton India produces now. The number is going to be the 500 million ton in 2047. Okay? So industrialization is bound to happen. Without that, our economics would not run. So we cannot be like the Amish people, right? We have to produce steel, we have to do the export, unless we would not get the foreign money to import the oil. So it's all interlinked. And meanwhile, we are really screwing up with the sustainability and the renewable thing. And very, very recently, the European Union has started the carbon border tax. I'm sure that you have probably read that into the newspaper. So, the carbon border tax tells you that if you are producing this much of carbon dioxide to produce that steel, that carbon dioxide does not stay in Durgapur or in India. It's also probably coming to Europe. So, if you produce that one, you have to pay me the tax when I import your steel to Europe. So basically, the Steel Authority of India Limited or Tata Steel or JSW, the leading steel segments, are losing a havoc money while they try to sell out that in the outside. And it is, last year I think it was just, the regulation was proposed, and from this year it is effective. That actually created a little havoc into the ministry level of India among the policymakers too, that okay, we were probably earning some money, now we have to really do our carbon dioxide. We just cannot take a pledge and come back and do nothing. So what they did, the Union Minister of Steel and Heavy Industry, the easiest thing they did, I mean, of course, this is probably the first step. I mean, always the first step is the low-hanging fruit. They made some nomenclature, okay, some taxonomy of the steel we are producing. So they say that if the CO2 emission is lower than 1.6 tons of carbon dioxide per ton of finished steel, then I will call your steel as a 5-star steel. So they have made some star category, the steel ministry. The 4-star is 1.6 to 2 ton, and 3-star is 2 to 2.2 ton. Okay. So depending on that, what 5-star or 4-star or 3-star your steel is, it does not matter what is the quality of the steel. It is basically that how much of carbon dioxide you are emitting while producing that steel. And according to that category of the CO2 emission from your exhaust pipe, your steel are actually ranked and your price of the steel will be ranked in that manner. Right?
Sir, just now you told that it is only.
I would really prefer if you call me Sounak.
Okay.
I mean, nobody gave me a knighthood.
2.5 times CO2 is emitted by producing 1 ton of steel. But here you are showing that 3-star for the one. I mean that is very low. Can it be valid? I mean the CO2 emission. Whenever we are producing steel, at the first time you told that it is 2.5.
Yeah, that's the scale. Yeah, around 2.5 to 2.4.
Here you are showing that 5-star will be given for 1.6 ton.
Yeah, so the idea is that if I call your
Can it be
steel.
changed?
No. So what does it mean? That you have to reduce your CO2 emission to come into the 5-star category of steel, which is now 2.5. It has to come down to 1.6 tons. Then only I will call your steel a 5-star steel.
So that is not fixed. That can be changed.
That has to be changed. The CO2 emission has to be brought down to, let's say that I'm JSW. I'm producing steel. And to tag my steel as a 5-star steel, I have to control my CO2 emission from the exhaust to bring it down from 2.5 ton to 1.6 ton. Then only my steel will be called 5-star steel. So basically that's the yeah. So basically you know the steel making technology, right? But then you have to now take care of the shit, the carbon dioxide. You just cannot let it away in the environment, which all these players were doing and not caring about the environment, right? So I told you that those percentages. Now let's consider on this segment, the steel production. Be it steel, I can take the cement industries example, I can take the aluminium industries example. The numbers will vary a little bit, but the effect on the environment is still the same, the carbon dioxide. So I am actually digging the coal and combusting that to produce the carbon monoxide and to run my blast furnace. That CO is pumped into the blast furnace in high temperature with the iron oxide to reduce the iron oxide to iron, right? This is the basic principle. So what I am doing, I am digging it, non-sustainable and non-renewable energy source, and I am producing carbon dioxide in the environment. The problem, what now comes the renewable resources, and then let's see that how this can actually change. It's not that we do not know, but then adopting it into the large scale is the And this, it's not just only the industry problem. If you really look at the thing, it is everybody's problem. The industry, the ministry, the policymakers, the legal team, and every one of us probably can contribute to see that how we can take a smaller step to the sustainability and can see a better world for our next generation, probably. Am I talking too slow? No, it's okay. Just whenever you feel that too much, I will take a break and can have a chat and then again continue. The solar energy, of course, is abundant, right? And particularly tropical countries like India can use that. But the challenge is that you need a fantastic quality silicon. The expenses are all there. Perfect, without defect, very crystalline semiconductor. The wind energy. Of course, the second one, the hydropower, the bioenergy, the geothermal energy, the ocean energy. Waves after waves are coming up. Let's use that one. The typology comes into the picture. But then the topic of discussion is the green hydrogen. The coke which we were using for the reduction purpose, right? The basic chemistry, the iron oxide, you all have studied this much chemistry probably, unless I can explain what it is. Or no, probably better to explain that it's a reduction process. Iron oxide is going to iron is a reduction process, and I'm using the coke. Instead of the coke, let's use the hydrogen to reduce that iron oxide. So I'm not dependent on the coal, I'm using the hydrogen. And when hydrogen combusts, it's producing only water. Environmentally completely benign, right? So the hydrogen is the source, and the other thing is that the carbon capture. We just cannot tomorrow probably go to generate the hydrogen for everything. And the hydrogen generation, let me now come and show a rainbow of hydrogen. It's just a gas, right? The first one on the left top of the periodic table, H2. But then it has a rainbow color. It's not that it really has a color, the gas doesn't have a color, but depending on that how we produce that hydrogen has a color code associated with it. Okay. The maximum amount of the hydrogen which is still being produced around the world is called the grey hydrogen. It's the most common type. Any clue where the grey hydrogen is coming from? Is really ironic that it is coming from carbon source. Still, the methane, okay? You take the methane from the earth and then you break the methane is what? There's a carbon and hydrogen, CH4. You break that into hydrogen. Now, why it is called the grey hydrogen? The process is called the SMR, the steam methane reforming. A small reaction, I cannot write it in a board. You take the methane, you react that with steam, okay? So CH4 plus H2O, the class 12 chemistry, just rehearsing a bit more. CH4 plus H2O giving you CO and hydrogen. Okay, this is the simple reaction. CO and hydrogen together is called the syngas, the synthetic gas. And then you separate that CO, you can do the Fischer-Tropsch synthesis to produce something else, but if you need the hydrogen,
Catalytic or thermal? It's breaking. Catalytic or thermal?
Both. You need the catalyst, you need the thermal energy. Catalyst you need to bring down the, again you are using the heat to keep the temperature high. So that's why you call it gray. It's not the green hydrogen. It's not a sustainable hydrogen. Absolutely right. You hit the crux of the problem. You are using temperature, you are putting energy, and then the CO what you are producing, again, probably you are making CO2 because you cannot let the CO go out. It's deadly poisonous, way more than CO2. CO2 will kill you the next generation, plus CO will kill you instantaneously. So you convert that to carbon dioxide and you just let it out. And that's the way the hydrogen is being produced now. And again, think that I am not using a renewable source. I am actually digging methane and breaking that into hydrogen. Now when I am using the hydrogen probably as an end user, I can see that okay, I am not directly polluting the environment because I am not using any fossil fuel. I am burning hydrogen and it's water. But think the source of the hydrogen, right? This gray hydrogen can turn into blue hydrogen when you take care of that carbon emission. So the CO of the CO and hydrogen is being produced, right? If you take care of the CO, then converted into carbon dioxide, and if you take care of that carbon dioxide, then at least one step is you are taking care. So that color gets changed to the blue hydrogen. So this, as step I said, the steam reforming of methane. The another step is called the dry reforming of methane. So in the steam reforming, what happens? You dig the methane, you pass the steam with temperature and catalyst. Instead of the steam, you put the carbon dioxide, which you do not want in the environment. So both are greenhouse gas. One is methane, one is carbon dioxide. You react the methane with the carbon dioxide, and you produce, so CH4 plus CO2 is giving you CO and hydrogen. And then this CO and hydrogen, as I said before, you can do the Fischer-Tropsch synthesis to make the synthetic fuel at high pressure and high temperature. Also, you can take care of the CO and can get the hydrogen. So if you are capturing that carbon dioxide while producing the hydrogen, it is called the blue hydrogen. Okay, the slide will be here, right? So anyone can actually go and, if you are interested later, you can see that what is the black and what is the brown. What is the pink is basically when you use the nuclear energy to get the hydrogen. Now, in the previous slide, I wrote here the green hydrogen, right? Now, green hydrogen is one when you actually produce it from water. Now, think of a situation that you have plenty of water in the ocean. You break that H2O, get the hydrogen. While breaking it, you need to put some energy, right? Unless water should not just simply give you hydrogen. That energy you cannot use again coke or some other non-renewable source, the solar. So in presence of the solar illumination, if you can break the water to hydrogen, this is the green route, what the hydrogen pundits are called. So now the goal is to get the green hydrogen. So India has actually made the 4 hubs. Pilani is part of one of the hub in Jaipur, Jodhpur, sorry, where the green hydrogen is getting prepared. It's not only just production, try to keep in mind, because if you want to use the hydrogen, if the hydrogen you produce fine, but it has to be transported, right? So the entire transport chain has to build up for the hydrogen. And so it's not only just the simple basic chemistry knowledge, it's the civil, it's the electronics has to come into the picture, because when you are breaking that, you need the solar energy and all those things. Everything is an integrated, not a standalone science can do this one. Now, hydrogen molecular weight is really, really low, right? So it has to be compressed and need to be taken from one place to other place. The trucks which are carrying now the oil will be carrying the hydrogen under high pressure. Pipeline we established again, but try to think that pipeline, the problem is that it has to be flow, because hydrogen is so light, it has to be flown, right? It's an energy expensive again. And with that high pressure, if you are carrying hydrogen, Right, it's a bomb, and with the Indian road, the trucks are going. so the entire system has to be renewed and an alternate system. So when I say that the net zero what India has taken, it's not only one person job. It has to be the entire society has to probably gear up to see that how comprehensively, collaboratively the thing can be done. And it's not only because somebody has taken a pledge, it's for the future, right? It has to be there, it cannot be any other way. Okay. So this, the another thing what I say, that let's say that I want to drive a vehicle by using hydrogen. When I enter a fuel station, I would not be buying diesel, I would not be buying petrol, I will be buying hydrogen. And my engine has to change first. This regular engine cannot run in hydrogen. So the entire technology has to be changed. And then, if you want to drive from here to the nearest place, Bardhaman, you have to have a fuel tank bigger than your car. Because hydrogen is really, really light, right? And you have to have a car behind, a tank behind, you are driving with a hydrogen there. And that too is highly flammable, extremely flammable and combustible.
Nature is also restricted.
Of course, right? So people are thinking of there is a generation problem, hydrogen generation. The bigger problem is probably the hydrogen storage. So people are thinking that if there could be any porous material, can take it, and with a slight heat, it will slow release the hydrogen to my combustion chamber.
Like calorie.
Huh?
Like calorie.
Palladium is not, unless we could have probably come out. People are struggling to see that what is the optimum material. You see, some people are proposing MOF and other things, metal organic framework materials, but still nothing is or in the lab still. Okay, so let's take a pause over here. I would really love to see if, am I boring? No. I think I have bored them. I know you have some words. Okay, sorry. Okay, that's why they're interacting more. But I would really love to hear anything, any question, with my knowledge if I can address.
Will you verify carbon pairing? Carbon pairing.
Okay. What exactly is that? Is that if I can save my carbon emission, then I get something back. Right? So basically the concept is that whatever you do, you have to take care of your carbon dioxide emission. Right? That's the fundamental thing, either the carbon credit or the carbon border tax or whatever the name I call. I just cannot let the combustion gases out, the flue gas out in the environment. So that's the fundamental thing. Small scale industries to the medium to the large scale industries. And that's the target. Carbon capture and using the green hydrogen. It's not that tomorrow you would come up and change every carbon source by hydrogen. It cannot be possible. So whatever so it is a step by step. First you do the carbon capture thing. And now the technique is called not just the carbon capture. So earlier it used to call the CCS. Not earlier now, so it's called. So carbon capture and storage. You capture, you put it under in the ground. Okay? The carbon dioxide, whatever is coming out from your blast furnace, you put it back. The issue is that you probably destroy the earth structure. I do not know what exactly.
How do you capture it?
Just put it back. Sequestration. Put it in the earth.
Oh.
Yeah. Or have some kind of, let's say that calcium oxide kind of a thing, right? It's going to be calcium carbonate. Those are used in the brick material. for construction of the houses too, right? You take the carbon dioxide, you convert it into carbonate and use it on the construction material. This is just the capture and storage. The other thing is that capture and utilize it. Some of those steel companies are actually to some extent doing it. So what they do, the carbon dioxide, whatever is coming out, they try to clean it. Because it's not only carbon dioxide, there is sulfur oxides, there is nitrogen oxides, there is methane, there is many other things, particulate matter. So let's clean the carbon dioxide, just take the pure carbon dioxide. People generally try to do it with the amine scrub and then compress it. Put it into the Sprite, Coca-Cola, Thumbs Up in the beverage industry. That is the maximum thing the steel industries are doing here. They are not earning much of money, but whatever the compressed carbon dioxide they are selling to Pepsi or Cola, they are bottling it. So basically, carbon dioxide is going into within you. Okay. But the next step, can we think of making something more useful? And
This is solvent.
okay. Anything else? Dry cleaning. Okay. What is that? So yeah, dry cleaning is using not water, some other. Any other idea? If you throw me, I would love. I mean, I would assume that we are, unless only he and I are talking. No one else. Any other idea of what we can do with this carbon dioxide? Anything? It does not necessarily has to be correct. Nobody knows what is the correct.
Sir, from the economic point of view, which one is more economic, the generation of solar energy or generation of hydrogen fuel?
That's a very good question. So, it all depends on where you are. If you have an abundant amount of hydrogen, solar light, then probably that is taken care of. If you have a good source of perfect crystalline silicon, if you have a supply chain of that is being taken care of. If you have the daytime mode and the nighttime rays, these are the three factors, right? To think that whether my solar energy.
From this point of view, if we look into that matter, even we import solar cell or some purified silicon from China or some Taiwan like that. So my question is, generation of hydrogen requires so much sophisticated instrumentation. So from that point of view, we are again using to generate the solar energy, to generate the hydrogen gas, we are using the same solar energy. So can't we directly use that solar energy instead of hydrogen?
Yeah, I mean, in general, I think the way people look at it, it's not only the one solution which probably fits all types of things. It has to be the multiple avenues. Everything, if it is depending on the solar, it would be a very much monopoly business because always the economics come to picture. As you have the right question, is that which is more economical? It will be that who is making all these solar chips, right? And that is the place which will be just getting the money. So while going ahead, I believe that the multiple avenues must be open, and that's how the policymakers also think. That it's not only one solution. Let's see the multiple renewable sources, renewable energy sources, how to make use of it.
Halogenization.
Okay, so valorization is basically is like rags to riches, waste to wealth, kind of. This is a fancy
Value-added product.
Yeah. Out of nothing. Out of not nothing. Out of a pollutant. Any other thing?
So earlier that you have
So in order to reduce that 2.5 to 1.6 that needed, do we add something to reduce the carbon? Because the strength will also.
Yeah, the carbon has to be captured.
So in that case, the strength will reduce. Say for the seal.
Oh, no. What I think, it is left to the industry that how do you reduce your carbon dioxide at the finally. So either you do the rest of the process as it is, but then let not leave the carbon dioxide, the 2.5 ton of carbon dioxide in the atmosphere. At least that part you reduce to 1.6. So maybe the steel making process is still the same. Everything is same. You are using the same thing, whatever your property of the steel you are maintaining. But that carbon dioxide, so this is at the final step when from the blast furnace, those flue gas which are coming, that you take care of. You trap it and then you give it. So that 2.5 you bring it down to 1.6, I will call your steel upright system. In that manner. Nothing to do with only the steel quality. If you use hydrogen, you are not producing the carbon dioxide. But then again, the hydrogen is only for reducing the iron ore to iron, right? Nothing else. So your steel will remain the same steel. Okay, now I was more or less trying to talk with the generic one. Now let me bore you some more with the details of the chemistry part, whatever we do. And we work on this particular periphery of in our lab, how to convert the carbon dioxide to some useful product. Okay, you capture the carbon dioxide, you utilize it. That's the goal. Okay, and so basically, I have around 8 to 9 PhD students and 2 postdocs who are working with me at my lab. And we try to do by the thermal catalysis, by the electrocatalysis, and by the photocatalysis. There are 3. So as I said in the beginning that I know how to make materials, how to study its structure, its surface properties, its morphological properties, its electronic properties. Use that and see that if I can do a small in the lab scale, convert the carbon dioxide to something. So what we first started doing sometime in 2019 or 18, I also cannot read. Maybe if the focus can be increased, it is visible. So some 7 to 8 years before, we started this. Is it blood? Is it blood? Huh? I do not know if it can be done anything. I don't think you can control it. Oh, yeah. Perfect. Oh, thank you. I mean, we should have requested you an hour back. Okay. Around, now I can read this 19. Around 7 years before we started, and zeolites, you all know what zeolites are, right? What are those materials? Are very highly porous material. And those porosity, so when you send a mixture of gas through those pores, depending on their pore size, they absorb one and let the other go. Right? So from a mixture of gases, you are capturing one, leaving the others. So we thought that if we can do that with the carbon dioxide in nitrogen mixture, in the laboratory you should not be getting the flue gas. We can simulate the flue gas, but ideally we thought that okay, the mixture of, because nitrogen 78%, 80% of nitrogen in the air. So when I leave it carbon dioxide skinny tiny amount, I tried to do that mixture and see that making a zeolite. We tried to make the zeolite from the rice husk. The rice husk, zeolites are aluminium silicon. So we tried to make that from the rice husk. And we tried to see that when we are passing, it can capture the CO2 So we passed it, you can see that this is the time scale, the 10 minutes. For 10 minutes there was no CO2 which was coming on the exhaust. So whatever was going and getting captured, nitrogen was only coming out. After 10 minutes when all those ports were blocked, the outlet showed the CO2 and went till the similar to the level of the inlet concentration of the CO2. So inlet and outlet become same because all the ports are now captured with CO2. So that's the first thing we tried to do. And while doing that, we thought that we cannot probably do a lot of engineering while making these ports narrow or bigger. Can we take some other kind of porous material? And that's where we landed with a particular category of material which are called the framework material. And those are called the metal organic framework. Last year, the chemistry Nobel Prize was actually given to people based on the metal organic framework. So the fantastic thing is that there is a graph, and this is the surface area. I told that so if a material is porous, the surface area will be high, right? As simple as that. And the surface area can go all the way up to 3,000 meters square per gram, which is like 1 gram of material will be having a surface area of a football field. That high. It's not that. It's just a highly porous. So how porous, and you can actually tune that very easily. It's actually based on a metal, and then there is an organic linker associated with it. So what we did is that we took zinc as a metal, and this was the linker, and by various synthetic technique we made this one. So we were getting, this is some electron microscope images, and the same material showed two different. One is something like a rhombic dodecahedron structure, and one is cube. So not cube exactly, you can see the picture, the truncated edge. So basically, you take a cube and then you chop off the sharp edges. You get the truncated edge cube. You further chop it off. You get this rhombic dodecahedron kind of a structure. So this is what we got. And we can actually, we learned that technique while making it. The student who was working with me now doing postdoc in US, he was the one who did show me through. So he learned the technique that how very controlled manner one can actually chop the morphology to. So basically what happens that when you do that, you actually expose some of the crystalline facets more. I would love to hear the conversation happening at the back. May I know the joke? I want to take part. No? I'm not sharing that joke with me. Okay.
What is the full form of GIF?
That is called zinc imidazolate framework. So there is zinc metal and imidazole linker, so that's the framework. So you can see that when we are passing this is the black one is the carbon dioxide adsorption desorption, and the colored one is the nitrogen. So basically what it means that when I change the pressure from 0 to 1.2 bar, I am absorbing more carbon dioxide compared to nitrogen and resorbing too. So adsorption, desorption. This is basically the isotherm what we call. So the thing is that my pore size of the material, because of that shapes and other things, I can control to selectively absorb the carbon dioxide more compared to nitrogen. That's my purpose, right? Teeny tiny amount of carbon dioxide and huge amount of nitrogen I can selectively take, and I can let the nitrogen go. and depending on the two different morphological structure, I can have a ratio. In one case, I was absorbing 9 times of carbon dioxide, 9 times of nitrogen, in another case 6 times. So basically that's I'm not going in details into the scientific. Okay. The image is the microwave heating, and the CH, we called that for the publication purpose, and the conventional heating. This is the technique. Where it is? Yeah. So in one case we were using just the muffle furnace, one case we used the microwave to make the framework material. Okay. I mean, I can go actually deep in chemistry, but for the larger audience, I'm not going till that part. It probably will go. I mean, I'm just trying to get the essence of the final result, that what we do in this line of the carbon capture and utilization and green energy. Okay. You remember this reaction which I was talking some time before, the methane and carbon dioxide producing the syngas. This is the gray hydrogen production. If you take care of this one, this would be a blue hydrogen, right, on the rainbow taxonomy of nitrogen. We work in this area too. So here, again, this is a little boring details. We took the lanthanum nickelate, LaNiO3, and so this is a perovskite structure, okay? And the another case we have taken the similar lanthanum, nickel and oxygen with a different structure. My basic background is actually the solid state and structural chemistry. So basically I try to understand that by changing a structure of a material, crystalline structure of a material, if I can see some different properties, okay? So that too, both the components are same, lanthanum, nickel and oxygen in both the cases. One is a simple perovskite structure, is a cubic shape. The other one is called the Rudolfson-Cocker structure with a layered structure, La2NiO4, K2NiA4 kind of a structure. Components are same, all the elements are same. I just wanted to see that by changing the different structural kind of a crystalline structure, if I can make this reaction happening with a different manner or not. So what you are doing, you are converting the methane, you are converting the carbon dioxide. So there is a methane conversion along the temperature, CO2 conversion along the temperature. You are producing the hydrogen and CO. Ideally, it should be 1:1, because if you can see that 2H2 with 2CO, it should be, the ratio should be 1. It does not happen in reality because of some other factors. I do not know that. The another problem is that when you produce this syngas, this methane which you crack, it actually deposits the carbon on your catalyst and it kills your catalyst. It's called the poisoning effect. So we also wanted to see that where the poisoning effect is good, I mean worse. We do not want the catalyst to be poisoned. Then every time in the reactor you have to change the catalyst if it is not having a longer life. So you can see that the LaNiO3 was actually better and La2NiO4 was not that. Again, I am not going into the details and explaining that what happens at what temperature. The essence is that what we do in our lab in this particular carbon utilization and the valorization technique, that we see the structural properties by X-ray diffractions and other technique. We can also run the in situ. So while the reaction is happening, we can actually throw the X-ray on the material and can see the minute structural changes happening on the catalyst during the reactions, and can actually come out and propose the plausible mechanism what can happen. This is the temperature dependent X-ray diffraction. We also can do the technique what we have in our laboratory is that when you have a material, you have a methane coming, you have a CO2 coming. These reactions is not a single step reactions whatever I have written. So multiple elementary reactions what happens, and finally the product of the syngas H2 and CO you get. So we all can actually probe those intermediate surface species We are studying the material structure. We can study the surface properties of the materials too, to come, and combiningly we actually propose the reaction mechanism. So that is something what we do. Okay, so the another what we have done in the similar line, it is not a perovskite structure. We took a fluoride structure. Actually, it's the pyrochlore, but essentially it's a fluoride. I will not now discuss that one. So the parent compound is La2Ce2O7, but it cannot react because you need the active site to make the methane and carbon dioxide react with each other. So the nickel concentration we constantly varied. We really can study the structural changes by the doping effect, what all happen with the doping, and we also did some theoretical studies. We do not do. We took the help of other research groups. We can study the micro strain, that by doping how much of the strain we are actually creating in the catalyst. We probably can also check the EPR data, the Ramanovs we can check. These are some electron microscopic images. And again, we check that by changing the nickel concentration in the catalyst, how effectively we can do this methane and carbon dioxide conversions to syngas. Couple of things what we study in any chemical engineering branch. You will see for any reaction efficacy to measure, the rate of the reaction has to be measured, the turnover frequency has to be measured, the selectivity has to be measured, the catalyst life has to be measured. All these things we routinely do and try to come up with the possible mechanism of the reactions. We also, I told you, right, the longer activity, so we ran it up to 50 hours, and these are some reaction mechanism. I am not going to tell you now that how exactly we came up. In some other discussions, if you are interested, we can take that up. So basically, in one line is that this is not a high pressure reaction. This is only the high temperature. As you have seen, the numbers are around 600 to 900 degrees Celsius. The reaction to take place. Okay. So we have those set up, flow reactor set up to make that happen. Now once you make the CO and hydrogen, I told you, you can do the Fischer-Tropsch to produce the long chain hydrocarbon, right, which probably can be used as a fuel. We also did one reaction. This actually work, we have done it with University of Bochum in Germany. Last year I was there for 6 months in a visiting international professor position. So in this one we directly wanted to make ethanol. Okay, so that was the target. Now why ethanol? From carbon dioxide we wanted to go to ethanol. How did you come to the college? To your bike. You put petrol in your bike. You don't get the pure petrol. That much of the crude oil import, the government thought that let's reduce this much import, mix some ethanol into it. And you are not changing any engine of your bike or your car, right? 80-20 mixture, still there's a lot of controversy, however, going on. One is that whether engine longevity. The problem is that ethanol can take the water and throw it into your engine. So that's the problem. Let's accept that what is the problem. Because government can go and tell you that nothing happens, but the reality is something else. So when you know the chemistry, there is a problem. The combustion value of petrol and ethanol are not same. Mileage will definitely come down, has to come down. Of course, the benefit are you do not depend on the crude oil import that much. 20%, that 520 million metric ton of number, whatever I have shown you, comes down by 20%. For the policymakers, it's good, right?
But the rate is not reduced enough.
Which is not reduced.
Right.
You and I do not have the control of it. We do not produce the petrol here. Only option is that completely change it to ethanol. Brazil is doing that. Make it to 80% ethanol. You do not bring petrol. You do not depend on the petrol price of the outside flow. the moment you do not produce, you cannot have a control on that. So come up with the technology which can actually tolerate 80% of the petrol.
So we can design the human based on totally.
Exactly. You are an engineer.
Yes.
You are an engineer. What?
Electrical.
Electrical. You are the one to make the engine better. To see that whether I can run a combustion engine with ethanol. No. Right? That's the crux of the problem. Can you come up with that? Ethanol production can be done. We are already doing it. The farmers are making this sugarcane bagasse, changing it to ethanol. Only thing is that probably your alcohol price will go up a little bit. but you do not cost a fortune on your petrol, right? So your choice. Whether you want to be drunk on Saturday or you want to save your money. so this is one of the work what we are doing.
But regarding that one controversy is also there in the Assam that has been saying that the factories which produce ethanol, so nearby pollution is also very much high for that zone. So is it true or is it?
I think I have triggered a place for the controversy. See, when you produce ethanol, huge amount of carbon dioxide you produce from sugarcane bagasse. How ironic it is, right? So, what we are trying to do now in the lab, okay, let the farmer, as you were asking, right? Shall we go to completely green hydrogen? Shall we completely stay with solar energy? The answer is not that either or, it's not 1-0 kind of a solution. It is that let's see that what is the best somewhere in the middle depending on all the available sources and everything. So you are right. Whenever I'm trying to make the ethanol in large scale from the food grains, multiple problems. One, your food grain scarcity. Second, you are polluting the environment while producing the ethanol. That ethanol, it does not yet have the engine completely, which can actually tolerate the ethanol till that extent. So you adapt one, multiple problems open up. But that does not mean that we should not adapt. Another technology has to come up. Yes, I'm just another technology has to come up to handle that problem.
So is it sustainable to adapt?
Which one?
This mixing ethanol or petrol or the pollution it is creating?
Now, this is another good question. Till now,
So near the speaker.
Near the speaker, sir.
So when you combust the petrol or diesel, there is a significant amount of nitrogen components and sulfur components are there. Not only the carbon dioxide, you are also producing the NOx and the SOx. When you combust ethanol, in the lab synthesized ethanol, it's a pure ethanol. You are only producing carbon dioxide. So, carbon dioxide, no change. Less harm on the NOx and the SOx component. Okay. That much only the change is happening. So, along with ethanol, the methanol is also one of the components. People are also seeing that if we can use the methanol. Because this was actually proposed, this ethanol economy, not in India, not in Brazil. It was proposed by another Nobel laureate in chemistry, George Ola. But he was little skeptical because mostly the people who would be making the ethanol are extreme alcohol consumption. Cautious about that one. But so then methanol is one way safer. We don't consume methanol. Now think of this situation. What you said is that ethanol production also, you didn't say, but the thing is that ethanol production also produces carbon dioxide. Twofold problem. One, we are dependent on the food grains. Two, again carbon dioxide. Can we not use this Tata Steel or DSP carbon dioxide and can convert that to methanol or ethanol? So at least it's a valorization, it's a circular economy, right? I told you that the CO2 emission has to come down by 2.5 to 1.6. Let's capture that carbon dioxide completely with your good solvent material, bring it, or there itself, put it under pressure and hydrogen and make it methanol or ethanol, right? Instead of depending on the farmer's food grain. So that is something which we are doing it. It's not again just only high pressure, high temperature is also high temperature, high pressure is also required. So the little bit of chemistry by changing the different morphology, we actually this blue line is the selectivity of methanol. Around 74% of the methanol selectivity we can actually achieve. I mean, we did it in our lab. That from carbon dioxide is a very simple reaction, right? Not a very complicated chemistry or anything.
You need hydrogen again?
Yes, sir.
So what from?
Crux of the problem. Where do you get the hydrogen from? The moment you get again the hydrogen, see, this is so interdependent. I'm really loving it that you are thinking and you are asking me questions. That hydrogen again has to be green. Then only this will be the net zero target. Unless again I will be polluting somewhere else, producing the dirty hydrogen and using it ethanol. As the company, what probably this transport minister's son is having and telling that, okay, all where from is he getting the hydrogen, right? So how much the policy and all those things happens, the fundamental has to be thought correctly. Unless it will be all eyewash. Until and unless I make green hydrogen, so again, I can go for ethanol economy, I can go for methanol economy, my hydrogen has to be the green hydrogen. I have to depend on the solar energy. Okay. This is a work which we are doing with the BPCL. You know BPCL, right? Bharat Petroleum Corporation Limited. They have a research lab in Noida, so we had a discussion. And we can actually convert the carbon dioxide to ethanol. You can see that 60% of the ethanol, 74% of the methanol is with one catalyst I have shown. This is 60% of the ethanol actually we can see. The conversion is only 20% of carbon dioxide I can convert to ethanol. There is a thermodynamic limitation, I cannot go beyond that. But then at least in that 20% of conversion, I can get 60% of ethanol. The crux of the problem is little bit of chemistry, where from the C1, carbon dioxide is only one carbon, right? You can make methanol again with one carbon. But then when you make from methanol to ethanol, there are two carbons. So you have to do a CC coupling. You have to make a bond between two carbons. And then you have to stop. It cannot go further. So you stop it and then hit it. Okay. This is something I want to show you another one. Now this is another proposal. The target of Niti Aayog actually told Government of India that by 2030, let's achieve this E20 petrol across the country. By 2015, India reached a lot. Good or bad will come, it has to be holistically decided. But something we did before deadline. Now the second approach, what Niti Aayog is proposing, and has been standardized by BIS, in your cooking gas, replace 20% by DME. Now what is the cooking gas is made of? LPG, which is propane. CH3, CH2, CH3. It's a simple structure. The middle CH2, take it down with an oxygen. In chemistry it's called the ether. CH3O CH3 has the exact same combustible value. Now why? Coming to your question. In the cooking gas, along with LPG you have NOx, SOx. You produce those things in the environment. When you produce the DME in the lab, it is just carbon dioxide, nothing else. Easy to capture that carbon dioxide because it is not mixed with other gases. So very soon, going forward, you would be seeing that your cooking gas is supplied with dimethyl ether, 20% of that. Okay, pressurized LPG, the propane with the dimethyl ether. Now, where to get the dimethyl ether from? NCL have recently shown. Now, think this is the ether, right? CH3OCH3. So, what they are doing? First, they are producing methanol, and they are dehydrating methanol. So, if you take 2 methanol, you take 1 water out from these 2, it will be turned into CH3OCH3. We thought that how differently we can do it. This is an NRF project for last 3.5 years we have done. We took the carbon dioxide. In a single step, we actually have produced a dimethyl. Now, generally, from the lab, it does not come to the newspaper, nobody cares. But what happened, at that time, you were unable to book your gas. Till now, 25 days restrictions to get the gas cylinder. So, all those newspapers started thinking that what happening are in the research laboratories. If not on the industrially final scale, at least let's see that the TRL 3 or TRL 4 level what is happening. Then we'll think of 5 and 7 and then taking it to TRL 8 for the large scale productions of the dimethyl ether. So this was one of our works that got some traction in the newspaper, in the Hindu, in the, I don't know which newspaper this is Deccan Chronicle, this is somewhere in Explorers or something. So this is something, some other work which they are doing. Okay. I think I would stop here. I can go ahead with some more. I thought of talking of photocatalysis. I thought of talking of electrocatalysis, where you do not need temperature and pressure. Photocatalysis, you do it with light illumination. The electrocatalysis, you do it with electrical energy. But that electrical energy cannot be from the thermal power plant energy. It has to be renewable unless the no energy gain. I am not going to talk about that because it will be too lengthy. And what I was told that the attention span maximum stays for 10 to 15 minutes. I really stretched your attention span for quite a long time. So I want to stop it over here. But any one of you, if you think that we can discuss, he has my number, my email ID. I can contact it easily. If you are planning to come to Hyderabad for a visit to the city, I can post you in my lab also. You can see whatever we do. Other than seeing the Charminar and having the Hyderabadi biryani, you can also see that what we do in our lab. And these are the people, and some more are not in the picture, who actually, all these things, whatever I speak around, they're the one who do it. And for anything you do, you need the money, right? So we have the money from NRF now, erstwhile CRB, now it is NRF, from DST, from CSIR. This is an industry, Hyderabad Batteries Limited, they also funded us for some time, now it's not there, for a project. The BPCL, I told you that we are working with BPCL on a particular work. This is the Indo-Canadian Research Center, ICTE. I have a project with University of Calgary and Pilani. This is the INA, the Indian National Association of Engineers. They funded us for a project. And of course, my host institute where I am from, they also pump in money in our lab to see the research output. And that's it. I want to finish it over here. Anything we want to discuss about the thing what we do in our lab? If you ask me, I will only tell unless I would not be continuing the discussion. And thank you so much for the attention. I know very hard it is to sit in this uncomfortable, comfortable only, okay, chair for so long and monotonously listening to all these jardins. But then, any comment, any questions, my knowledge.
What are the basic you take for the?
I work with mostly the oxiding materials, the various kind of oxiding materials. Now for electrocatalysis, definitely we use some nanometals as well, the nanoalloys. Very recently, we are exploring the high entropy alloys.
Particularly for carbon dioxide as well, the material. So what are the things?
You know, the best carbon dioxide adsorption material is LaNi5, an alloy. Nothing, no other material compared to
ALANI5.
nobody can make it.
Oh.
And it's not industrially, I mean, in a large scale, you cannot produce it. So it has to be an alternate material. And lanthanum, again, rare earth. You depend on China.
So how do you get it?
No, to some extent, lab scale you can buy it, but then when you try to do it in a large scale, it's a problem. Yes, sir.
Sir, as you said, in Brazil, 80-20 research economic technology over there. So the compatibility with their engine.
I think they have made some changes in it. And they, surprisingly, I was going through the price of this ethanol making. I have not shown you the data I had. Generally, we say that India is a cheap country, its resources are cheap, cheap labor. Our ethanol per liter actually costs higher than Brazil and US. US produces ethanol from corn. Brazil produces ethanol from sugar. We produce ethanol from molasses, mostly. Our production cost is higher. Our 1 liter ethanol production even from molasses are actually higher than what US and Brazil. So we have to come up with a different technique. It cannot be just
Sugarcane is possible.
sugarcane is of course costlier than molasses.
Sir, have you tried to implement your lab findings in any real industries?
There's the one with BPCL we are doing, but in the lab, the technical term is called the technology readiness level. So in a lab, we reach to 3 or maximum to 4. And in industry, when you see the finished product in the market, which it comes, that is in the TRL 7A. So from TRL 3 to TRL 7 is called the valley of death. Because you are good in the science probably, you can do it in the lab scale. But then when you need to have a mini pilot or pilot and then a complete phase, it has to be a hand-holding between the academia and industry. Without that, it cannot happen. And that is significantly less in a country like India. So, we are doing it with BPCL. We also did something with HBL. But then, there has to be a different policy to the industries that, see, you just cannot buy the technology from first world country. And we constantly pumping money. Pilani don't get money from the government of India, but IISc Bangalore, all the IISers, the IITs, government heavily pump money to these places. Why these technologies are not, indigenous technologies are not coming to the industries? Which of the industries are actually buying the Indian origin technology? Probably nothing. So the policy has to be changed. So government probably should act like a priest between the to be married couple kind of thing. Academia also don't like to talk to industry because we think that we know everything. We are independent. What we think when we are in academia, mostly communicating our results to the journals. People come and pat us. Wonderful work. In a smaller scale, maybe the promotion and all those things. But then, and then industry don't care. Industry thinks, oh, there's a ready-made technology already in the market, let's buy it from US or Japan. But then those countries are actually working the freeze laboratory, right? It's mandated to have our CSIR is bound to do that work. The name is that but then again that is very much academic kind of an institute. Turned into, unfortunately, an academic kind of institute.
resource.
Unless, again, there's a sustainability problem. Unless, I told you, right, among all these funding agencies, only HBL and BPCL. BPCL is again the semi-government kind of thing, right? And HBL is completely private. So, if that handholding is not there, it's not a sustainable thing. You need money to do research. And it is not only ROI tomorrow, return on investment tomorrow. Industry thinks in that manner, that if I am pumping money today and tomorrow I will get something that cannot happen. You have to wait, you have to have the patience, and then only things can change. Yeah. Okay, any other question? No? Okay, so then thank you. Thank you for your attention. It was a lovely speech.
Thank you very much for your patience. Actually, in a nutshell, Sir has described so many things. We have learned that this concern started in 1979 in the conference. After that, Kyoto Protocol, Paris Conference, and finally we have learned so many things, so many new terms like rainbow hydrogen. It's really interesting things that we have learned. And also we have learned how the porous materials can be designed so that it can absorb CO2, and finally in his lab or in his laboratory, how he is designing the CO2 absorbent materials. So it's a nice thing. Finally, we want to thanks again to our respected distinguished speaker, Sounak sir. Thank you very much for a wonderful session. Now we are having with us Jamal Singh sir, who is the treasurer of our society. Thank you very much for in this session. Now I would like to take a moment to congratulate our distinguished speaker sir, Sounak sir. Thank you very much.